Hello students of statics, this is Dr. Dan Baker, and today we're going to start a new chapter, and I think this is actually a really exciting chapter because we're going to start using all these tools developed in chapters 1, 2, 3, and 4 to now solve rigid body equilibrium problems. Okay, so we've solved problems so far, equilibrium of particles, and we've learned all the tools we're going to need to solve equilibrium of rigid bodies. Now we're going to bring these things together. And so I think it's worthwhile when you start any new topic to reflect on what you already know, right? You don't come into any class empty-handed. You have a whole bunch of knowledge from your previous classes and life experiences. So reflect on this question. What do you know about free body diagrams? What do you know about reactions from supports? And what do you know about equilibrium equations? Now, there'll likely be some things you don't know, and it's good to write those things down too. But write down what you know, maybe write a few questions of things you don't know. In the interest of saving internet storage, I'm just going to have you pause the video instead of being quiet for 3 or 4 minutes. So go ahead and pause the video, write down some notes on these topics. Thank you for your reflection time. So now moving forward as we look at these different terms. So in a nutshell, I could actually bring together these 3 bullet points into a couple of statements. The first statement is that a free body diagram is the graphical representation of all loading. Now remember, whenever we say loading, we mean forces plus moments, okay? So of all loading on a body. So this is the same definition that we had back in chapter 3. The second point that I'll make here brings together these terms reactions and supports and gets into the equilibrium equations bit as well. And that is that reaction forces slash couples, so basically reaction loading, are engaged by action forces slash couples to maintain equilibrium. And the reason that I write out this statement, it may seem a bit obvious, but what we're talking about here is that there's certain forces and couples. These action forces are external and or body forces. Okay, so when we're talking about these action forces, things that are being applied to a body. When these external forces are applied, or there's a body force, a weight applied, we need other forces to keep the system in equilibrium. Okay, and so those other forces come from the other bodies, the other things, the other supports that are touching that rigid body, and so we call those reaction forces coming from these supports. So the reality is if the action forces are equal to 0, there's nothing being applied. Okay, now this would also have to assume that your body is weightless. Then we don't need any of these reaction forces. They can exist. You can think that even if you had a balloon that had an equal amount of helium in it, essentially to cancel out its weight. Okay, so fundamentally you have a weightless balloon and it's just floating in space. You could attach all the supports you wanted to it, and you won't need any of those supports to keep it from moving, right? Because it is already in equilibrium within itself, having a 0 net action loading, right? Any of these external or body forces. But as we increase the weight of that balloon, as we start pushing on it, pulling on it in different ways, we're going to need some reaction forces to counteract those. Okay, so that's just contrasting action and reaction. So as we think about how that then relates to equilibrium, this idea of equilibrium is really related to motion. Okay, there are two types of motion. And these types are translation and also, as you probably know from physics, rotation. So if there are two types of motion, there also must be two types of equilibrium. Essentially, we need to constrain the motion, both for translation and also for rotation. And so if we're looking for equilibrium for translation, that comes down to an equation that is sum of all forces, and forces are vectors, is equal to mass times acceleration. Accelerations are also vectors. And for rotation, the general equation there is sum of moments is equal to the capital letter I times alpha. Now let me define these different terms here. I think you probably fairly well understand the translational terms. Sum of forces equals mass times linear acceleration. For the rotational, we have that I is defined as the mass moment of inertia, which you may have been exposed to in physics. It's fundamentally a body's resistance to rotation in this format. And then alpha is the angular acceleration, okay? So let me add a couple more statements here. So sum of force equals mass times acceleration. But when A, our linear acceleration, is equal to 0, we can simplify this equation to sum of all forces is equal to 0. Same equation we use in chapter 3 for particle equilibrium. And then here, when we have angular acceleration equal to 0, so when alpha as a vector is equal to 0, and keep in mind, let me add a little note here, this is angular acceleration, then we end up with an equation sum of all moments equal to 0. So these are our two fundamental equilibrium equations in statics. We will use these over and over and over again. And so they're essentially telling us that we're limiting the motion, or we have an equilibrium, a balance of forces that will prevent any translation, and a balance of moments that will prevent any rotation. Okay, so those are fundamental equations. In addition to learning about summing moments and summing forces, we'll also end up covering moments of inertia. Now in statics, we'll specifically talk about area moments of inertia, and we'll talk more about that. That's toward the end of the class. In dynamics, we end up needing to use mass moments of inertia, so we'll revisit mass moments of inertia in dynamics. All right, so that's the general umbrella under which So that's the general framework that we'll be working with here in chapter 5. So to keep progressing forward, let's talk a little bit more about free body diagrams. I guarantee all of you will have something to learn about free body diagrams. Free body diagrams for rigid bodies are another level more complex than free body diagrams for particles. Okay, and so we talked about that free body diagrams are the graphical representation of all forces and moments which act on an object. Okay, let me say that again. Free body diagrams are the graphical representation of all forces and moments which act on an object. Okay, they're going to be used in physics and statics and dynamics and solids and structures and machine design and fluid mechanics and any course where essentially we're doing kinetics, relating forces to motion. Okay, so just a reminder here as we talk about the term kinetics. So when we talk about the word kinetics, which you'll get to know and love in dynamics. This is defined as relating forces to motion. Fundamentally, sum of forces equals 0 and sum of moments equals 0 are kinetics equations. It's just that our motion is 0. Okay, it's the most simplified type of motion that you could have in that things are at rest. Okay. Now, these steps to create a free body diagram. And these are expanded in the engineering statics textbook. Now, there are some different steps out there. You're going to see a ton of similarities between them if you read different textbooks. This is the steps that we use here in this class. And the first is to isolate. We need to isolate the body, and I'll put in parentheses here, or group of bodies away from the rest of the system. Okay, essentially we need to draw a line around it, cut away everything that that body or group of bodies was attached to. So the difference between a body, so a single rigid body, like your book, your calculator, your pencil, or a group of bodies, if you took a stack of books, okay, 4 of them stacked on top of each other, it turns out we can create a free body diagram of that stack of books, just like we could take a free body diagram of the entire car versus one tire or the steering wheel or a different piece. Okay, so we can take a group of bodies all together. And one other thing to emphasize there before moving on to step 2 is make sure when you isolate this body, you draw a separate drawing. Okay, so it's not your problem sketch. You're not adding forces on top of your problem sketch. You're drawing a separate representation of that body. It can be a simplified representation. If it's a complicated body, you can draw it as a blob, you can draw it as a square, you can draw it as a circle. It can be a simplified representation as long as it has enough geometric reality that you can add the forces that you need to as we go through these next steps. So step 2 is that every free body diagram needs an axis. So we need to establish an axis system. Maybe I should put even simpler terms. Instead of establish, just put draw. Draw an axis system. Now, many problems, maybe 85, 90% of problems, will use a horizontal X and a vertical Y. As you get into dynamics later, we'll use different axis systems, tangent normal and polar and some different things. But for right now, typically Cartesian, X and Y. Number 3 is to load the body. And this is basically saying whatever forces are given on that body in the problem sketch, make sure to bring those along, okay? So load the body with external loads plus weight. Number 4 is to add reactions. From supports. And these supports, you actually cut them away back in step 1. Okay, so add reactions from supports. You cut away when isolating. And step 5 is to add needed dimensions for computing moments. Now, depending on who you have teaching statics, if you have me for statics, it turns out that I probably will never, or I will say, I will never mark you off for not having step 5, having dimensions. I'm actually fine with you looking at the dimensions from your problem sketch, but you do need to do 1 through 4. Okay, those are basically what make up, in my mind, an appropriate free body diagram. 5 is more of a convenience. If you want to add those dimensions, the problem with adding too many dimensions on a free body diagram, it can muddy the water of exactly the forces and couples that are applied to a body and basically make it a little bit harder to see what's going on. Okay, so a review of these, we want to isolate, we want an axis system, we want to make sure that we load the body with external loads, add our reactions, and add our dimensions. Okay, so those 5 things: isolate, axis, load, reactions, and dimensions. You could think of them as the 5 fingers of free body diagrams if you want to memorize them that way. So you could check all your free body diagrams. And then we get into the remaining steps to solve the problem. Okay, so the remaining steps to solve. So I could call this number 6, and that would be to write our equations of equilibrium. And these equations of equilibrium are directly based upon your free body diagram. They're basically the mathematical representation of all forces acting upon, all loading acting on an object. On a 2-dimensional problem, we have up to 3 equations of equilibrium. Okay, and the reason for that, and you can read about this more in the engineering statics textbook, is that there are 3 degrees of freedom for a 2-dimensional body. For a 3-dimensional body, it turns out there are 6 degrees of freedom. Therefore, we need 6 equations of equilibrium. And we also know that equations are related to unknowns. And so for 2D, we can have 3 unknowns. And for 3D, we can have up to 6 unknowns. Now, as we continue learning in statics and then into dynamics and other classes, we'll add more equations than just these equations of equilibrium. But for now, we're kind of stuck with just these 3 equations for 2D and 6 equations for 3D. And so it's really also to say that if you create a free body diagram that has more than 3 unknowns for a 2D problem, revisit your free body diagram before writing any equations, because you will not be able to solve for any more than 3 unknowns in 2D or 6 unknowns in 3D. And then step 7, which is probably the step you're most comfortable with, because it's really just doing some math, is to solve these equations for your unknowns. So it turns out many of our unknowns on our equilibrium problems turn out to be the reactions. It's very common for us to know what the loading is, to know what the geometry is, to know what body we're trying to look at. And it's really this step 4 here that a lot of the effort is required to figure out not only what kind of reactions are available from supports, but then also trying to solve for those unknown terms as you move forward. So this should lay out the overall system. In the upcoming video, we're going to dig into the reactions themselves. So the reactions essentially are the forces and moments which come from the physical supports. Okay, and so we'll look at those in the upcoming video. I hope you're having an awesome day.